Okay, so in this video we're going to look at a very practical concept, and you've probably experienced it in your life, so it might hit home. That's the idea of the maximum tolerable tractive effort. Essentially, there's a limit on the tractive force that you can exert, that the wheels, I guess, can exert on the surface, and beyond that limit, you start to skid. Now, you'll probably have noticed that when it's wet outside, if it's been raining and you're at a traffic light, and all of a sudden you floor your gas pedal, you'll probably notice that your vehicle skids a bit. It's definitely skids in the winter if there's snow on the ground, and we're gonna try to, in this video, understand what that is and how we can kind of understand the different parameters that influence this skidding, and why certain vehicles skid more than others, and why some seem to not skid at all, and then sort of set a limit on, according to whatever conditions you have, set a limit on what that tractive force should be. So we can start first with the idea that Ft should be less than or equal to mu Wf, and Wf is this weight on the front axle, and Ft should also be, or I should say or, it's one or the other, it's not both. And this is for a front wheel drive, and this is for a rear wheel drive. And these are the two most common cases, I guess, although nowadays you have four-wheel drive, and that is some variation of the two, which I guess is, you would probably consider some combination of the two depending on how they're distributed. But that's not the purpose of this video. And this expression, I mean, these expressions are basically the high school FF equals mu Fn, where this is the force of friction and this is the normal force, right? So the weight on the front axle is the normal force that the front of the vehicle experiences. So if you have a front wheel drive, that's the force of friction that needs to be overcome. It's along the same concept, I guess. And so mu is the coefficient of friction. Maybe we can mention that. So this is coefficient of friction, and then Wf and Wr are the weights as they are indicated here on the front and the rear axle. So we can show, well, not show, I guess, but there are a number of there's usually tables for maximum possible coefficients of friction. So for instance, on asphalt you might have, it's like 0.8 or 0.9, snow is around 0.2, gravel is like 0.6, and so mu changes depending on the conditions. And so as designers of vehicles, it needs to be clear that these vehicles will operate under different conditions. Usually if the market in which these vehicles will operate is subject to different conditions like that. For example, if you're selling a vehicle in India, chances are you don't need to sell a car that can drive through a bunch of snow, right? You probably want it to not be able to drive through snow, because that would be a waste of any consideration of all your resources. It's like, because chances of having some major snowfall in India where you would be driving through like a foot of snow or something, it's probably impossible. Well, I guess there's always a chance, but very low chances of that happening. So alternatively, if you're going to sell a vehicle in Canada, you would want it to be able to drive through those snowy conditions, because they're very common in Canada. So it's an important consideration, I guess, is the point we're trying to make here. So you can show, it can be proven that Wf is equal to Lr over L times W, and W is the weight of the vehicle, H over L, and H is the height of the center of the mass, and Ft minus Fr, and Fr is the rolling resistance. So this is rolling resistance. So we don't confuse that with F capital R, which is the road load, which are not the same thing. Then you have the weight on the rear axle, will be Lf over L times W plus H over L, Ft minus Fr. And again, rolling resistance. And so Fr is the total rolling resistance, and remember that this rolling resistance Fr is equal to remember it's like C0 plus C1 V squared and all that stuff, and we combine that as CR, if you recall in one of those earlier videos, and this is times mg, because that's the equation. And mg is basically the weight of the vehicle, right? So we can probably apply that simplification at other parts of the overall result as well. So LR is the horizontal distance, so from the center to this rear axle, and then this LF is from the center to the front axle. And these distances usually aren't the same. So that's something else to consider as well. So you can combine these equations and you can produce a set of results. So you can basically combine, let's say, this FT and this WR, and you can produce a set of results basically for rear wheel and front wheel drives. So for the front wheel drive, so let's say here front, so for front wheel, and then we'll say here rear, and then we'll write the expressions. So for the front wheel drive vehicles, you want FT to be less than or equal to mu W LR plus H times CR divided by L plus mu H. And for the for the rear wheel vehicles, it'll be FT is less than or equal to mu omega LF minus HCR divided by L plus mu H. And so these expressions will give you what the maximum limit on these should be. So why don't we just take an example of a real, I guess, or a practical situation. So let's say you have a vehicle and it's front wheel drive and it's on dry asphalt. So let's say dry asphalt, and that means mu is equal to 0.9 and LF is equal to 1 over 3L, and LR is 2 over 3L, and L itself is equal to 2.75 meters, and H is equal to 0.75 meters, and CR is equal to 0.01, and let's say that the weight of the vehicle, let's say it's a 1500 kilogram vehicle, so that's 1500 times 9.81, and that is 14715 newtons. So given all of this, and given that this is a front wheel, let's say it's front wheel drive. If it's a front wheel drive, you can use the expression here for this FT here at the top, and you can literally just plug everything into that and see what you get. So FT, for some reason it doesn't go right away. Okay, FT is going to be less than 0.9 times 14715 times 2/3 times 2.75 plus 0.75 times 0.01. All of that divided by 2.75 plus 0.9 times 0.75. You get FT should be less than or equal to 7117 newtons. Now, what that means is if you apply any force greater than 7, did I say 7.117? It's 7,117. I don't know if I said point. Anyhow, 7,117 newtons of force. So basically, if you have an initial accelerating force that is less than that, there won't be any skidding. And we'll look at some other examples where we'll see how much initial tractive force is required, and you can kind of relate all of that stuff into this. But this is a good metric to understand how much force you can apply without the vehicle skidding. So what did we do here? We looked at the standard, I guess, illustration we have here, and we established based on these friction model, is essentially what it is, it seems, that the tractive force should be less than that if you don't want it to skid, initially at least, and then you can adjust the tractive force later on. We had these equations, and I know I kind of pulled these out of thin air, but you can essentially derive them based on some simplified models of mechanics, which is not really the point of this course, or these topics. And so I guess it's better to skip over that. The thing to take away is that you can have these limitations if it's a front wheel or a rear wheel drive, and based on that, we kind of did this really quick little example to understand, based on some standard parameters, because this is dry asphalt, these are fairly reasonable numbers to see with a vehicle. It shows you, it gives you a relative measure. Now, of course, it's impossible to know what 7,117 newtons of force actually is, but you can convert that. I mean, if you were to actually go down to it, you can convert that into a torque. You can convert that. You can use that to get a power, to determine what your speed can be, what your acceleration can be, the torque, what torque you need, based on what torque you need. If you're using a certain type of machine, like a DC motor, let's say, how much current do I need to give my motor? And so you can really get into some very interesting types of analysis just by understanding this number. Although physically speaking, this number means very little to most people, because nobody knows what 7,000 newtons of force really looks like, I guess. Well, I guess some people might, but I certainly don't. In any case, I hope this video was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.